Have you ever smelled something so strong like a formalin or a nail polish remover that instantly walks up your brain?
Funny thing, those sharp smells actually came from compounds that love hanging around in perfume, cleaning products, and even food.
These mysterious bonds all share one powerful bond, a carbon double bonded to oxygen. Sounds simple, right? But these tiny bonds makes them very reactive.
Now here's the catch. Some of them like staying in the end of the carbon chain, while others prefer hiding in the middle. See the personality differences. And because of where he stays, one of them gets excited and reacts easily, while the others stay calm and cool like kids on butter. You can find them almost everywhere, from your perfumes, preservatives, medicines, and even your scented candles. They might smell nice, but they mean serious chemistry business.
So any guesses what these two powerful groups are? Here's a hint. They act fast, smell strong, and are the stars of organic chemistry. Come, learn it with us. Good day, everyone. We will be presenting Aldehydes and Ketones.
What are aldehydes and ketones? These are organic compounds with structures carbon-hydrogen-oxygen bond, where R and R represent carbon-containing substituents respectively. Aldehydes and ketones are classes of organic compounds that both contain carbonyl functional group, which is the carbon double-bonded oxygen, which is characterized by a carbon atom double-bonded to an oxygen atom. The carbonyl group is one of the most important functional groups in organic chemistry due to its reactivity and occurrence in many natural and synthetic molecules. This aldehyde and ketones will be further discussed in the next slides. In aldehydes, the carbonyl group has one hydrogen atom attached together with either a second hydrogen atom or a hydrogen group, which may be an alkyl group or a containing benzene ring. Aldehydes are special kinds of chemicals that have the same ending part called the carbon-hydrogen-oxygen bond. So in every molecule of an aldehyde, its ending part, if this is the molecule, this is the ending part, which makes it an aldehyde. This is the carbonyl group, which is the carbon-hydrogen-oxygen bond. The CHO part means there's one carbon holding the hydrogen atom and the oxygen atom. This part in the ending, this must always be present at the ending of a aldehyde to make it an aldehyde. Here is another example of an aldehyde, which you can see in the whole molecule. You'll find the carbon-hydrogen-oxygen bond at the very end of the molecule. This. You'll find it at the very end of the molecule. So, no matter how big or small a molecule is, the most important part of it that makes it an aldehyde is the ending part, which must contain the carbon-hydrogen-oxygen bond at the very end. This. Always keep that in mind.
So, hello everyone. For today's topic, we're going to be tackling about aldehydes and ketones. So, for everyone's information, aldehydes and ketones are organic compounds that both contain a carbonyl group, which is a carbon atom double bonded to oxygen. This carbonyl group is what gives them their special properties. For aldehydes, the carbonyl group is always found at the end of the carbon chain, meaning its terminal. It is attached to at least one hydrogen atom. Some examples are methanol, ethanol, propanol, and 2-methylbutanol. On the other hand, ketones have the carbonyl group located in the middle of the carbon chain, making it internal. It is attached to two carbon groups instead of a hydrogen. Examples include propanol, butanol, and
In an aldehyde's general structure, aldehydes have a special part called the carbon-hydrogen-oxygen bond. The carbon in the middle, one oxygen and one hydrogen, and one other group, or we sometimes substitute it with R or represent it with R. Those are carbon containing other groups. This is what a general structure of an aldehyde looks like. So you have carbon always in the middle with one hydrogen, either double bonded or single bond oxygen. So this is always the general structure of an aldehyde inside a molecule. While for the ketone is only a carbon double bonded with an oxygen atom. Ketones have no hydrogens present in their general structure. This is a general structure of a ketone. You see that there are only carbon and oxygen atoms present in a ketone. There is no hydrogen present. To simply put it, when hydrogen is present, we call it aldehyde, and when there is no hydrogen present, we call it ketone.
Both aldehydes and ketones are polar molecules because oxygen is more electronegative than carbon, which causes a partial positive and negative charge. This polarity also affects their boiling points and solubility. In real life, aldehydes like formaldehyde are found in biological processes, while ketones like acetone are common in industrial uses such as sulfates. The main difference between the two lies in the position of the carbonyl group. Aldehydes have it at the end, while ketones have it in the middle. That's it.
Hi everyone! Today let's talk about the nomenclature of aldehydes. Aldehydes are organic compounds that contain carbonyl group, a carbon atom double bonded to oxygen that is always attached to at least one hydrogen atom. Aldehydes are considered the most important functional group. They are often called formyl or metanyl group. The name aldehyde comes from alcohol dehydrogenated, meaning an alcohol that have lost hydrogen.
Aldehydes and ketones are organic compounds which incorporate a carbonyl functional group, C equals O. The carbon atom of this group has two remaining bonds that may be occupied by hydrogen, alkyl or aryl substituents. If at least one of these substituents is hydrogen, the compound is an aldehyde. If neither is hydrogen, the compound is a ketone. This means that both aldehydes and ketones have a carbonyl group, which is a carbon double bonded to oxygen, or C equals O. The difference depends on what attached to the carbonyl carbons. If one of the attachment is hydrogen, the compound is an aldehyde. But if both sides are carbon groups, it becomes a ketone. Aldehydes are found at the end of the chain, while ketones are found in the middle. For example, ethanol is an aldehyde and propanol is a ketone. So, the main difference is the placement of the carbonyl group and what atoms are attached to it.
In the system, aldehydes are named by replacing the E at the end of the alkane name with al. For example, methanol, also commonly known as formaldehyde, ethanol, also known as acetaldehyde, and the last one is propanol. Because carbonyl group is always at the end of the chain, it automatically gets the position number 1. So no number is needed in the name. In common naming, the parent name comes from the carboxylic acid, but the ending IC acid is replaced with aldehyde. So for example, acetic acid will be called as acetaldehyde. The carbon next to the carbonyl group is called alpha. The next is beta and so on. This helps describe their substituent positions. If the aldehyde moiety is attached to a ring, the suffix carbaldehyde is added to the name of the ring. The carbon attached to this moiety will get the number 1 location number in naming the ring. Aldehydes are common in nature. Vanillin gives vanilla its scent. Cinnamaldehyde gives cinnamon its spice. And benzaldehyde gives almonds its aroma. So remember, aldehydes always have the carbonyl group at the end of the chain, named with the suffix al, and often smell surprisingly sweet. In the system, aldehydes are named by replacing the E at the end of the alkane name with al. For example, methanol, also commonly known as formaldehyde, ethanol, also known as acetaldehyde, and the last one is propanol. Because carbonyl group is always at the end of the chain, it automatically gets the position number 1. So no number is needed in the name. In common naming, the parent name comes from the carboxylic acid, but the ending IC acid is replaced with aldehyde. So for example, acetic acid will be called as acetaldehyde. The carbon next to the carbonyl group is acetaldehyde. The carbon next to the carbonyl group is called alpha. The next is beta and so on. This helps describe their substituent positions. If the aldehyde moiety is attached to a ring, the suffix carbaldehyde is added to the name of the ring. The carbon attached to this moiety will get the number 1 location number in naming the ring. Aldehydes are common in nature. Vanillin gives vanilla its scent. Cinnamaldehyde gives cinnamon its spice. And benzaldehyde gives almonds its aroma. So remember, aldehydes always have the carbonyl group at the end of the chain, named with the suffix -al, and often smell surprisingly sweet.
Naming ketones. The IUPAC system of nomenclature assigns a characteristic suffix of 1 to ketones. A ketone carbonyl function may be located anywhere within a chain or ring, and its position is usually given by a location number. Chain numbering normally starts from the end nearest the carbonyl group. Very simple ketones such as propanol and phenylethanol do not require a locator number since there is only one possible site for a ketone carbonyl function. The common names for ketones are formed by naming both alkyl groups attached to the carbonyl then adding the suffix keto. The attached alkyl groups are arranged in the name alphabetically. So this means that when we name ketones in the IUPAC system, we always use the ending 1. For example, if we have 3 carbon chain with a carbonyl group in the middle, we call it propanone, which is commonly known as acetone. The position of the carbonyl group is important, so we number the carbon atoms in the chain starting from the side closest to the carbonyl group. This helps us identify where the ketone is located. If the carbonyl group can only be in one possible place, like in propanone or phenylethanol, we don't need to write a number anymore because it's already obvious. For common names, we use the names of the 2 alkyl groups attached to the carbonyl carbon and add the word ketone. For example, ethyl-methyl ketone means one side has an ethyl group and the other side has a methyl group. And remember, we always arrange the alkyl names alphabetically in common naming. Naming aldehydes and ketones in the same molecule. As with many molecules with 2 or more functional groups, one is given priority while the other is named as a substituent. Because aldehydes have a higher priority than ketones, molecules which contains both functional groups are named as aldehydes and the ketone is named as an oxosubstituent. It is not necessary to give the aldehyde functional group a location number. However, it is usually necessary to give a location number to the ketone. In this part, it means that when a compound has both an aldehyde and a ketone, we need to decide which group has the higher priority. According to the IUPAC rules, aldehydes have a higher priority than ketones. That's why the compound will be named as an aldehyde and the ketone will be named as an oxosubstituent. For example, if the ketone is on carbon number 3, we write 3-oxo, followed by the name of the aldehyde. It's also important to note that aldehydes are always found at the end of the chain, so we don't need a number to show their position. But for the ketone, we usually include a number to show exactly where it's located. So overall, when naming molecules with both groups, we always focus on the aldehyde as the main functional group, and the ketone becomes a substituent.
The physical properties of aldehydes and ketones. First, let's talk about the boiling point. Think of it this way. The bigger the molecule, the harder it is to boil. You can see here the general rule. As the molecule gets heavier or longer, the boiling point goes up. Look at this example. Methanol boils way below freezing at negative 19 degrees Celsius, but ethanol boils at positive 21 degrees Celsius, which is close to the room temperature. Why? Because boiling is all about breaking the sticky forces between molecules. The stronger those forces are, the higher the boiling point has to be. So what are these sticky forces? They are called the intermolecular forces. We have the 2 main ones here, the van der Waals dispersion forces. And this is the basic force all molecules have. The longer the carbon chain gets, the more surface area and electrons it has, making the molecule stickier to its neighbors. That's why the boiling point increases with the carbon count, the van der Waals dipole-dipole attraction. This is the extra important force. Aldehydes and ketones have a polar carbon-oxygen double bond like a tiny magnet with a positive and negative end. These magnets lined up and pull the molecules together much tighter than non-polar molecules, like simple hydrocarbons. The result, aldehydes and ketones have much higher boiling point than simple hydrocarbons of the same size because of this extra magnet-like attraction. Of solubility, small aldehydes and ketones do mix with water because the polar carbon-oxygen double bond can form hydrogen bonds with water. They are basically helping each other out. That's why small ones like methanol and propanol are called miscible, meaning they mix in any amount. As the carbon chain gets longer, let's say 6 or 7 carbons, the non-polar part of the molecule gets too big.
Good day everyone, I am Irish and today I'll be talking about structural isomerism with a focus on one of its main types, the chain isomerism. This topic is very important in organic chemistry because it helps us understand how compounds that have the same molecular formula can actually be different substances because of the way their atoms are connected. So, structural isomerism. It happens when two or more compounds have the same molecular formula but their atoms are arranged in a completely different order. This means that the number and type of atoms are the same, but the way they are linked together is different. Because of these differences in structural isomers have different physical and chemical properties, such as the boiling points, melting points, and reactivity. In short, structure determines identity. Even a small change in how atoms are connected can create an entirely different compound. So, isomers and its rotation. Now let's look at the first diagram. It shows butane, which has the molecular formula of C4H10. There are two drawings that look different, but these are not structural isomers. Why? Because the only difference between them is the rotation around a single carbon-to-carbon bond. In organic molecules, single bonds can rotate freely. So even if a molecule looks different after rotating, it's still the same compound. This clearly explains that if you can change one structure into another simply by turning it, they're not new compounds, just different orientations of the same molecule. To form a true structural isomer, you must actually break and reconnect, changing how the atoms are joined. So, remember, rotation doesn't make a new isomer, only a change in bonding does. So, structural isomers. It happens when atoms are connected in different order. That's when we get structural isomers. Each isomer has the same molecular formula but a different structural formula, meaning the arrangements of the bonds is unique. This difference changes the compound's identity and sometimes its property. So now let's move on to the chain isomerism. Chain isomerism occurs when compounds have the same molecular formula, but their carbon chains are arranged differently. Some may form a straight, while the others are formed branch chain. A perfect example is butane, the C4H10. Butane has two chain isomers, the N-butane, where all 4 carbon atoms form a straight chain, and isobutane, also called 2-methylpropane, where 1 carbon atom branches off from the main chain. Although both have the same molecular formula, their structures and even their properties are different. For instance, N-butane has a slightly higher boiling point than isobutane because their straight chain molecules can pack more closely together. So chain isomerism is all about how the carbon skeleton is built, whether it's a straight or branch, while keeping the same number of atoms overall. So, additional example. Another good example of chain isomerism can be seen in pentane, which is the C5NH12. Pentane has 3 chain isomers, the N-pentane, which has a straight chain of 5 carbon atoms, Isopentane, also known as the 2-methylbutane, which has one branch, and mu pentane, or the 2-dimethylpropane, which has two branches. Even though all three have the same molecular formula, that is the C5H12, they differ in structure and physical properties because of how their carbon chains are arranged. So, in conclusion, structural isomerism occurs when compounds have the same molecular formula but different structures. One type of it is called chain isomerism. It happens when the carbon atoms are arranged in different ways, either straight or branched. Even a small change in how atoms are connected can make a big difference in compounds' properties and behavior. So, the arrangements of atoms truly defines what a substance is.
So how do we differentiate ketones and aldehydes? So we have an example here. An aldehydes is referred as RCHO, since R means rest of the elements, and CHO, CO, the carbonyl group, the carbon double bonded to oxygen and a branch of hydrogen atoms. And in ketones, we have the RCOR, or referred as RCOR, since the carbonyl group sits between the two elements, or the carbon double bonded oxygen sits between the two atoms or elements. Now we move on to the last type of structural isomerism, the functional group isomerism. Basically, the isomers of functional groups, they belong to different families of compounds or different homologous series. Our highlight is the carbonyl group, since our group topic is aldehydes and ketones. Carbonyl group is a functional group that contains carbon double bonded to an oxygen atom. Now we have an example of position isomerism here with the molecular formula C3C7 And note that, as we said a while ago, an atom or a group of atoms changes position within the molecule in position isomerism. So in this molecular formula C3C7 it can be either be named 1-bromopropane and 2-bromopropane. 1-bromopropane if the bromine is placed at the first carbon atom, and 2-bromopropane if the bromine is placed at the second carbon atom. Now we move on to the example of position isomers in aldehydes and ketones. But in aldehydes, they rarely form position isomers because the carbonyl group is always placed at the end of the carbon chain. So we focus on ketones. So we have the molecular formula C5H10O, and with that molecular formula in position isomers, we can form various structure or chemical structure depending on how you place the carbonyl group. And we have two examples here. The first example, we have the carbonyl group placed at the second carbon, and the second example is the carbonyl group is placed at the third part of the carbon atom. And that is how position isomers works. Now we move on to the second type of structural isomerism, which is position isomerism. In position isomerism, you might see molecules with the same molecular formula, same carbon skeleton structure, but they're different in the location of their functional group, their subsequent, an important group of their atoms, and even their carbon bonds. In other words, even if the main carbon chain remains the same, you will see the changes of their important group of atoms within molecule. And also in position isomerism, if you see same number type of atoms, their chemical and physical properties slightly differs because the location or the changed location of their important group of atoms or functional group affects how the molecule interacts with other substances.